Now I'm going to start talking about the p-center problem. We'll go into the nonlinear version of the p-center problem for tree networks. Unfortunately, the nonlinear version, even though it's very general, is not yet solved for general networks case. So one of you might want to tackle that problem later if you wish to. But other than the nonlinearity, which gives quite a bit of generality to the problem, we will also talk about a certain duality aspect which is not evident in the problem itself, which comes out actually if you somehow start investigating other properties of the problem. So such things usually come out as a byproduct without you expecting it, but you should have a keen eye for actually noticing things or for recognizing something that has some special property. You should be able to recognize that when it comes out or when it makes itself evident. Well, if it's evident, that's going to be fine, but if it just reveals a little bit of it itself, then it may not be that easy to recognize such things. So let me give you, actually, we had an example problem that we started talking about. I had this tree network, so let's just look at that particular example. And I'll try to give you some insight on some of the later stuff where that comes from. Okay? This is the tree network we had. And we made a mistake last time because we were in a hurry. And so I hope we won't make any computational mistake right now. This was the tree, vertex 1, vertex number 2, number 3, number 4, number 5, no, number 6. Number 5 is this one up here. And my weights are 1, 3, 1, 2, 1, 1. This is just a made-up example, so we'll see how it comes out. And I gave you the distance matrix, and using the distance matrix, we computed those numbers, beta ij's, where beta ij was defined to be the ratio of the distance to the sum of the reciprocal weights associated with that pair. This was the definition. Dij is the distance between the vertex pair I and j. And with that, our Bij matrix was the following. And we know from previous theory that one of these numbers will be the p-center optimal objective value for any value of p between 1 and 6. Actually, when it's 6, of course, the objective value will be 0. But when P is between 1 and 5, it will be one of these numbers. Now, we had the ordered list, 6, 6.67, 13.33, 15, 15 and a half, 1875, 20, 24, 25, 26.4, 28 and 28 and a half, 31, 33, 31.5, and 33.5. All right, so what we wanted to do last time, and I kind of went through it very quickly, we wanted to make a search over this list, a binary search. And for every value we pick from the list, that's a possible R value, an an R value for the covering problem. So for that R, once you pick a number R from this list, I don't know, did we give a name to this? I typically call it capital R. Okay, so whenever you pick a number R from capital R, what you do is you solve a covering problem which consists of the minimization of the cardinality of capital X subject to the closest distance between X and VI is less or equal R over WI. This is for every I. And X is a subset of T. So for that reason, whatever number you pick from the list, you define your R over WIs as your possible string lengths, and you attach or you fasten a string of length R over WI at vertex VI. We did that for one particular value we picked from the list. I forgot which one was it. Was it 20? Okay, so we did that for 20, except that initially I located 3, which was a mistake because actually as soon as you located the first one, you should have assigned some of the possible strings to that one, which when removed would lead to a 2 facility location rather than 3. We did that correction, so I'm just refreshing your memory on that. And besides, the camera should also know that. Otherwise, of course, we do not want to mislead anybody. Okay. All right, so with this, for R equals 20, it turned out that the covering problem, optimal objective value, turned out to be how much? 2. And that tells us that actually our two-center objective value, the optimal objective value, will be something less than or equal 20. We do not know which. It's possible that it could be the optimal value, but it could be also less than that. It certainly will not be greater. All right. So in that case, of course, you can simply focus on the values from 6 to up to 18. From 6 up to 20. You should include. Well, actually, you've already solved that, so you can just get rid of that, and you can restrict your search to 6, from 6 to 18.75, and then whatever new value you pick from the truncated list, you just apply the same procedure, okay? Until eventually your list contains exactly one number, at which point you know you will have found your optimal solution to the p-center problem. Does that make sense? Okay. All right. That I'm not going to do. But for the exam, you should be prepared to apply such things quite in an efficient way. Okay? You don't want to lose too much time with that. All right. What I want to do is, I want to do something else now. Just play with it. Now, when p equals 1, what do we know? What is the best objective value for p equals 1 from what you've learned so far in this semester? Largest. If it were unweighted, we would look for the longest path, but this is weighted, and these numbers are what I called before alpha ij's, I think, and you looked for the maximum alpha ij, and then that value determined the actual one radius, the best possible value for the one center problem. Okay, so in this case, of course, the largest one is 33.5. So this tells me that R1 is 33.5. Okay? And that one is determined by which pair? Where is it? Okay, this pair, which happens to be 3 and 5 pair. So this number is B35. It's determined by the vertex pair 3 and 5. So how do I locate? Well, what you do is you pick that value, 33.5, and then you look at the weight for vertex 3, which is this one, and vertex number 5, which is this one. And then the weights are 1, actually, in either case. So what we do is, in the tree, I presume I assign a string of length 33.5. I'm not going to assign any other strings except also this one. This is number 5. This is number 3. This is the critical pair. And this one will have a string of length, how much? 33.5. Because the weights are 1 in either case. Okay? So then, when you look at this path between them, how much is this? 20. Now, forget all the other upper bounds on the coverage of other vertices. If you only wanted to cover these ones within these string lengths, you would pull this string tight towards the other one alongside the path. This one also alongside the path. They would meet at exactly 1 point because that's the sum of those two is 67, and that's exactly the length of this path, which means that they actually meet right at the midpoint. Okay, there's no way you can move to either side. Exactly. Otherwise, again, they would have met in exactly one single location, but it would not be the midpoint, it would be the weighted midpoint, so to speak. Okay? All right. So wherever that one is, 25 plus 8, so you go 8.5 units this way, I guess. The remaining one is 22 minus 8 is 14, so that's going to be 13.5. All right. And I know that as soon as I locate that particular point at that point, I know that the other ones will be covered. How do I know that? Because we proved it. That's how I know it. Otherwise, of course, we don't know it. Okay? I mean, there's a theorem which actually we proved, which was originally proved by Francis and Deering, and that was the theorem. The largest one, the critical pair, determines a location which actually covers everybody else as well. Okay. So, here's the question for you. If I'm interested in covering these vertices with an R value which is a little bit smaller, then what am I supposed to do? Yes, of course, because when you wanted to make your R a little bit smaller, obviously these two critical ones will not be jointly covered, right? Because this string will be a little bit shorter, that string will be a little bit shorter. For that reason, their endpoints will not meet at a point. So whatever is covering vertex number 3 will not be able to cover vertex number 5, and likewise for the other one. Okay? So obviously, in that case, if I want to go, for example, for p equals 2, I have to separate these two vertices, separate their coverages, assign them to different facilities. So in that case, let me do a site, or let me keep track of what I want to do by writing the vertex numbers of these vertices. So the critical pair initially is 3 and 5, and the appropriate Bij value for that is 33.5. And that's a good value or a feasible value for p equals 1. But if you wanted to reduce it further, meaning that you increase your p by at least 1, then this one will be assigned to a separate center, and that one will be assigned to a separate center. Okay? Two different centers. That's why I just wanted to keep track of what's going on with that. So, forget the binary search now. The next possible value is 31.5. Here's the question for you. Can I actually cover all my vertices using this particular R value with only 2 centers? Yes? How do you know that? Just a second, one at a time. Who was the first? Okay. Oh, I see. Oh, I see. Okay, okay. Yeah. Okay, but other than that, okay.
Well, I was thinking about if we can cover whole vertices with a radius of 33.5 and we increase the centers to 2, then approximately about half of 33.5, but approximately, would cover.
Okay, so you're just relying on your intuition that it should be almost halfway between. Okay, so of course, that could be true or may not be true, but nevertheless, you have a point. Okay, let me have you.
You can move 2 units left and 2 units right from the exact solution.
From this one?
Yes.
2 units this way, 2 units that way?
Yes, then it will do the job.
Why 2 units? Because that's the difference, okay.
It will do the job.
I see. So if you move 2 units away from here, you will be within the appropriate R value of that one, and the other ones will be okay, I guess. That's what you're thinking probably. And for that one also, the other ones will be okay. All right. So the next value, which is 31.5, where is that? 31.5 is this one. The critical pair for that is, well, the pair for that is 2 and 5. So this tells me that what does that tell me? I just made a record of this. This particular number tells me that if you wanted to jointly cover 5 and 2 together, then the best you could expect to do is to have an R value of 31.5. Does everybody agree with that? Because these beta Bij's exactly tell you what the value of the joint coverage would be if you had only 2 vertices under consideration. Okay? If you don't agree with me, that's 2 and 5. Where's vertex 2? Vertex 2 is this one. Now, how much is the weight for vertex number 2? That one is 3. So we're talking about 31.5 divided by 3, if I wanted to go with that value. This one would be 31.5 as well, because it has a weight of 1. That I'm no longer considering that, so let me just erase that. Now, I don't know how much 31.5 over 3 is. Nevertheless, it's something around 10, well, a little bit over 10. So you will be going as far as somewhere here. 10.5? Oh, okay, 10.5. Well, actually, you can go 10.5 distance units this way or that way or that way. I don't know, but it can go in many different ways. But this one will be 31.5, so plus 10.5 will give you how much? 42.
Yes.
42, is that 42? Yeah, 22 plus 20 is 42. So they would again meet at exactly 1 point, which is in a way, the weighted midpoint of that path length. However, if you want to do better than this, which means that you need to make this smaller a little bit. In that case, of course, 5 and 2 cannot be jointly covered by the same center because they will not meet. Okay, so whenever I put an edge like this in the graph I'm constructing here, an edge means those 2 vertices should be covered separately by different centers. Okay? Right now, of course, 3 and 5 will be covered separately. 2 and 5 will be covered separately. So one possibility is I can assign 3 and 2 to the first center, wherever it will turn out to be, because there's no edge between them, and 5 to the other one. Okay? So things look okay. Of course, this is a very intuitive way of, or heuristic way of looking at this. Okay? We're not proving anything. We're just sort of developing some judgment about what may be happening. All right, next. Can we do slightly better? 31.33. I don't know. What is that pair due to? 30, where is it?
3 and 4.
3 and 4. Oh, okay. 31.33. 3 and 4. So 3 and 4, that's going to be 31.33, which is very close to the previous one. Nevertheless, it's strictly smaller. That would mean, again, if you want to cover 3 and 4 together, then that's going to be the best you can do. However, if you separate them out, for example, if you assign 4 to the other side, then you don't have to jointly cover them, so you can possibly do better. All right. What is the next one? 28.5, which is induced by vertex pair 3 and 6. Now again, if I cover 3 and 6 together, that's the best I can do. But if I decide to cover them separately, which means I can assign 6 to the second one, that would permit me to perhaps go down further in the coverage radius. Of course, we're not checking really anything, if we're really going for the right thing or not. Nevertheless, we're just going with our feelings. Next, 26.4 induced by, did I make a mistake there? That's supposed to be a 4, right? Is that what you have from the previous lecture? Yeah, that's supposed to be 26.4. So that's 2 and 4. 2 and 4. So there we go. Can I cover them separately? Well, 2 is on this side, 4 is on the other side, so I don't have any particular problem with this. Next, 25. That's going to be 1 and 5. 1 and 5. Again, you want to cover 1 on x1's side, the other one is on the other side. Okay? If you want to go further down. Next, 24. Which one is that? 2 and 6, okay. 2 and 6 is 20, how much was it? 24. So our 2 and 6, well, they are already on separate sides, no problem. Next, 20, which is due to pair 1 and 6. That's 20. 1 is here. Did you say 1 and 4? Just a second. No, but let's pick this one. Let's go one at a time. This is, which one did I pick? 1 and 6, okay. So 1 is this on this side, 6 is on this side, so I'm okay. Now it's going to be 1 and 4. Again, that's 20. But 1 is here, 4 is here, so again, I don't seem to have a problem. I can go even further down. Next, 1875, which is due to 2 and 3. 2 and 3, 18.75. At this point, you do have 2 and 3 together. And if you want to separate them out, well, unfortunately, well, either 3 goes there or 2 goes there, but 3 is being rejected by the other ones, at least by one of them. And 2 is also, well, if you pick 3 here, who is it rejected by? By 5, because there's this thing here, okay? If you wanted to move 2 on this side, 2 is also rejected by 5, okay? So, unless you want to create a new center, you cannot really separate them out, because everybody's, actually you would get worse. If, for example, 3 moves here, if you happen to pick it up on this side, due to 3 and 5 being jointly covered, you would have a value of 33.5. You don't really want to do that, okay? So, that's not a good decision. It's much better to keep it here. If you move 2 to the other side, you would have an R value of at least 31.5, so that's not a good decision. So the best thing you can do is to keep them together and live with 18.75. That's the best. And anything better than that will cause a new center to be located. So something happened here. There's a critical point, and we are able to somehow detect that. Well, actually, I know this is what's going to happen. So, but something critical happened, and if you weren't really keeping track of these things, how would you have noticed about this thing? Does anybody see anything special happening here? In other words, if this list were really too large and we were not able to process what's really going on, nevertheless, there's still something going on here. Does anybody have a feeling for that? Huh?
We have a circle of old number of outside.
Which one is that?
Like
What is the circle?
3, 2, and 5, or 3, 2, and 4. We cannot color them with 2 colors, then we need 3 colors.
Okay. So you...
A little bit graph theoretical, but...
Okay. Well, you've got something there, yeah. So...
We need 3 colors to color them.
And colors, in a sense, stand for the number of centers you want to locate. Maybe that's what prompted that. Yes, we do have a certain node set here such that each node is being rejected by some other node. Well, actually by every other node in that set. Okay? So that the best you could do is, since everybody is rejecting everybody else, the best you could do is to keep the smallest ones together and separate the other one out. Does that make sense? Okay. So that is certainly a worthwhile conjecture. In other words, you can conjecture here that R2 should be this much. It cannot be smaller than that. So if I can actually do the job with 2 centers and still cover everything within this, then I do have a feasible solution. Of course, whether or not we can really do it, we don't know yet. What do you think? Can we do it or not? Without using the covering algorithm. Since I'm asking the question, I guess we should be able to do it, yes. But what is the reason is a little bit not clear at this point. How would we do it? Actually, precisely in this way. This is why I kept this on the side. Here, you've got 3 and 2 together. 1 also needs to be here due to the fact that 1 is rejected by at least one of these guys. Okay. 5, 4, 6 should be together. Does this account for all the vertices? In this case, it does. So all you have to do is you want to find a one-center solution for these vertices by themselves and another one-center solution for these. And that one has nothing to do with this one. So everything else drops out. So if you wanted to find a one-center solution relative to 1, 2, and 3, what would be the value you would get? Well, in that case, we're talking about B12, B13, and B23 values. The largest of them will give you the value. How much is B12? From the, I can't see, 6. And B13 is 15.5. and B23 is actually 18.75. So I know that the one center solution for this subset of vertices will give you this much coverage. That's the best you can do. For the other part, you need B45, B46, and B56. How much is B45? 13.33. B46? 6.67. B56? Same? 15. So this side has a smaller value. Well, so of course, then your R2 is indeed exactly this, because a one-center solution to either one will tell you it's going to be a best solution. Can you do better than that? The answer is no, because to do better than that, you have to somehow resolve this subset into two parts, but any other resolution, rather than keeping 2 and 3 together, will cause you to go up to at least 31.5 or 33.5, which is much worse. Okay? All right. So let's continue. Wow. Actually, we're out of time, so let's continue after the break.